computer. All right. Okay. So Kepler's third law. So that's the Kepler's third law. That's also called the law of periods. Let me also make this as capital L. All right. So there are two things in here. So let me first of all draw the shape in here, right? So we have the, first of all, the central object. So that's the central mass. I'm going to call the central mass as the capital M. Yeah, let me write capital M in here. So we have a satellite in here. So I'm going to call this as little m. So that's the satellite mass, right? And then what else? So there's the semi-major axis length, right? Let me also draw this in here. So this distance is 2s. So this time I'm going to call the semi-major axis length as with little s. Semi-major axis length. Okay. I'm just giving the essential quantities in here. Okay, so why do I use S for semi-major axis length? Because letter A is not useful because we usually use letter A for showing the acceleration. So as a result, people get confused by this, right? That's why I'm using a different symbol. That's the reason. And the textbook also does this, right? The semi-major axis length is basically is shown by this thing. Okay. So in any case, the Kepler's third law says, well, there's one thing in here. So it's the period. So let's say that's the period of the orbit. Period of the orbit. Okay. So in any case, so it basically says that the period, I mean, this is not the original statement, but I'm going to state it like that. So the period of orbit, of the orbit, T depends only on the semi-major axis length S and the central mass. Okay, so we have talked about this thing. So especially these kind of orbital parameters, anything that's related with the motion of the satellite does not depend on the satellite's mass, right? Satellite's mass is actually irrelevant. So there are only two parameters in here, the semi-major axis length and the central mass. So somehow the semi-minor axis length in here, or the eccentricity of the ellipse, somehow doesn't enter into the picture for some reason. So for the orbital parameters, only the semi-major axis length somehow is important. And so as a result, that's basically the second part of the statement. So basically says that T squared is proportional to S cube. Okay, that's the original statement, but I'm just going to add to this with the proportionality constant depending only on M. Okay, so basically what I'm saying is that T squared is equal to K times S cube, right? Where this K depends only on the central mass. Okay, that's basically the statement, but I mean, that's the main statement in here. But I add these kind of details in here, right? So that's the only thing that we should say. So as a result, I mean, let's say that for sun, let's say, there are different planets perhaps in here. So that's the first planet, for example, and then, I don't know, the second planet in here. So that's the second planet, Venus. And I don't know, the third planet might be something like that. I don't know if it is really the case. So that's the third one and so on. If you just consider all the other planets, basically for each planet, we have the same constant in front. So basically this constant of proportionality is the same. And as a result, we have this relationship for all planets, right? I from 1, 2, 3, and so on. People usually write it down like that. So for each planet, if I just compute the ratio between the square of the period to the cube of the semi-major axis length, that's going to be the same for the second planet, S2 cube, and the third planet, and so on. Okay. In any case, I mean, that's basically the statement. And sometimes we actually write it, instead of doing it like that, we usually compare the orbits of two planets, for example. In that case, we basically take the ratios of the two periods and then say that this is basically cube of the ratios of the two semi-major axis lengths, right? We can also use it like that. So whatever you want, okay? Okay, so let's just say it like this, but we can actually deduce this easily, right? So, but perhaps the critical statement in here, so if the period of the orbit depends only on the semi-major axis length for the orbital parameter, then we can deduce this, okay? So let's say it like this. So suppose that I have some kind of a satellite in here. Suppose that let's say it like this. If the semi-major axis length is S, then find the period T of the orbit. Right, let's just consider this as a problem. How do we solve this, right? For this orbit, these two quantities are given. One of them is the semi-major axis length, S. The other one is the central object, the mass of the central object, okay? And we would like to find the period, okay? How do we do this? That's basically very simple. Right? I mean, the main statement in here is that if I consider any other orbit in here where the semi-major axis length is the same, right? I mean, if the S value is going to be the same, then the other orbit also has the same period. So as a result, I'm just going to use this to actually compute the period, because I cannot compute the period in here because I know that the speed is changing. The speed is different everywhere. It's not a uniform circular motion. It's a very complicated motion, okay? So as a result, solving the problem for this orbit is difficult. But if I somehow show that the period for that orbit is the same as the period of a circular orbit, then by computing the period of that circular orbit, I can then solve this problem. So basically, that's what I consider, right? So I just imagine there's a circular orbit in here. There's another orbit in here. So that's not a circle. I'm going to use this thing, all right? So that's probably better, right? So I'm going to think about, imagine an orbit in here. It's a circular orbit. So let's say it like this. this is if this is a circular orbit with radius s, okay, so it's a circular orbit with radius equal to s. In that case, this orbit have the same, it has the same semi-major axis length. It is s, and so therefore these two orbits have the same period. Okay, so both orbits have the same period. Okay, I'm basically using the fact that the period depends only on the semi-major axis length. So that means by using this, I'm finding a circular orbit with the same semi-major axis length. And if I find a period for the circular orbit, then the problem is solved. Okay, so as a result, I mean, this is something that I imagine in here. Right? And so as a result, we solve the problem for that orbit. So that's a circular orbit. Again, circular orbit. In that case, I just basically imagine a satellite. So let's also say this is an imagined satellite. It's not real. Okay, so let's say that it is moving with speed v. We have done this calculation before, but let's do it again. Okay, so F equals ma, or the net force is equal to ma. Right? Force is equal to the force between the central object and this imagined satellite. So therefore, this is gmm divided by s squared. What's the acceleration? Well, the mass is little m. What's the acceleration? It is v squared over s. I see that the satellite's mass cancels, but it never enters into the equations. So I find v to be equal to the square root of gm divided by s. And then from here, I find a period like this by using this equation, 2 pi s divided by the period is equal to speed. So from here, therefore, the period is 2 pi s over v. And so therefore, this is 2 pi s over the square root of gm divided by s. Yeah, whatever. So at the end, we get that the period is equal to 2 pi over the square root of gm multiplied with s to the power 3 over 2. So that's the relationship. So that's the answer to that question. Okay. Again, let's come back. That was the original question. So, I mean, if we have an elliptical orbit with the same major axis length, s, and the central, yeah, let me add this. So the central mass is equal to capital M, then find the period in terms of these two parameters. So that's the answer to that question. But to find that question, I mean, I somehow artificially considered some kind of an, imagine a circular orbit with the same major axis length. Knowing that they have the same periods, I just compute the result for that thing. Okay. So I can go further. So I can then compute t squared in here. So that's 4 pi squared divided by g times the central mass times s cube. So from here, you can see that, well, that's the coefficient of proportionality in here. So as a result, the period squared is proportional to s cube. So that's something that we have deduced before. So that's one of the statements of the Kepler's third law. And the second statement is that this coefficient of proportionality in here just depends on the central mass. I mean, it doesn't depend on, for example, its size, whether it's a star or I don't know, it's just a small object, or doesn't matter. It's going to be the same. It will just depend on the mass. Okay. I'm going to add one more thing in here, all right? So why is there a square and cube in here? Why do we get these kind of relationship? Right? Note, I mean, this relation can also be obtained by using dimensional analysis. Okay, because we have like these four quantities. One has the dimensions of time, one has the dimensions of length, one has the dimensions of mass, and then some kind of a constant of nature, which has some certain dimension expressed in terms of these fundamental dimensions. So as a result, there can be only one possible relationship between them, right? And the relationship should be some kind of a, I don't know, let me write something in here. Some, let's say, dimensionless constant times the power of something as the power of length, the power of mass, and whatever. I mean, we have solved these kind of problems before. So it appears that in that special case, these particular powers are given by this relationship, okay? And because of this is actually universal. It can be applied anywhere. I mean, even for example, exoplanets, we see that the same relationship is satisfied, even though the situation is completely different. Or for the situation where, I mean, for this collision of two black holes, for example, we essentially get the same kind of a relationship, right? That's basically how we measure, how people measure the mass of the black holes, because they could measure the period. I told you this before. The period was like about like 1/75 seconds. 1 second divided by 75. So by using this information and then by doing some other estimations about this distance between them, they can say something about the mass, right? So as a result, this is a very nice, simple relationship, which basically applies anywhere, more or less anywhere. Okay. So I'm just going to solve a number of problems in here. So I'll just start with this. And then if I have time, I'm going to come back to the question that I asked you before. This is actually one of the classical questions. Right. Comet Halley. Has a period of, it's not a planet, but it's a comet. So that means that it's an orbit with a very high eccentricity. Okay, so it basically comes back once in every 76 years. The last visit was like in 1980 something, 86, 85, I don't remember, but when I was young actually. So it was around that time in 80s. So as a result, just count 76 years after that. So it will become visible after that many years. So it will come near, right? So Comet Halley has a period of 76 years. So at its closest approach to the sun, right, it has a distance of RP that's equal to 8.9 times 10 to the 10 meters. Right? Given that Earth-Sun distance is, let me call this as, I don't know, little r is 1.5 times 10 to the 11 meters. So I think this is also called 150 million kilometers, right? When people quote this number, they just say it like this. So like this is 150 times 10 to the 6. So that's 1.5 times 10 to the 8, and a kilometer is 10 to the 3 meters. So you basically get this number. So given that Earth-Sun distance is given by this, so there are some questions in here. A, find the aphelion distance. RA, so distance when it is farthest from the sun. Okay, and part B, what's the eccentricity of the orbit? Okay, so this comet is basically nothing special. So let's say that this is the Earth's orbit. So that's E. So E is the Earth. And this orbit is something like this. All right, it's an ellipse, but this is, it has a very high eccentricity, right? So that's Sun, and the yellow thing is Halley. Okay, so it moves very fast when it is near Sun, obviously. But in any case, with that speed, it just goes too far away. And at these far places, of course, it's going to be moving slowly. So whatever it is, we don't care about this. So does this have anything to do with Earth? No, it doesn't have anything to do with Earth, because these are two different planets. Well, this is just a comet, but in any case, they don't have anything to do with each other. But I'm using Earth to compare some certain things, right? So for Earth, I know that the period, so the period of the orbit of the Earth is basically 1 year, right? And semi-major axis length, yeah, let me write it down like that. Yeah, I think I'm going to write it down like this. Semi-major axis length. So I'm going to use SE for that. That's basically given by this little r quantity. So that's 1.5 times 10 to the 11 meters. And for Halley, that's why I call this. So the period is also known, so that's 76 years. And the semi-major axis length, so let's call this as SH. This is unknown. So by doing a simple proportionality, I can find this. By finding that, I can also find the other distances in here. So let me actually show the other two distances in here. So that distance is RP. So that's RP. Yeah, I'm going to use a different color for that. Sorry. So it is that distance. I'm going to call this as RP. This is the perihelion distance. And that distance is called RA. Okay, aphelion distance. So whatever, I mean, I'm just going to form the equation. So, but first, I need to find the semi-major axis length of Halley's orbit. To do this, I just compare the orbits of the Halley and the Earth. And by doing this ratio, I can actually find the relationship. So the relationship is this. The square of the ratio of the periods is equal to the cube of the ratio of the semi-major axis lengths. I somehow just took this relationship and then take the ratio so that the proportionality constant basically is gone, which means SH over SE is given by the 2/3 of the that thing in here. So that's the ratio is 76. That's the nice thing about the this information in here. both of them are given with the same unit. I don't need to convert them to seconds. So let me do this calculation here. It is 76 to the power, where is the power? Yeah, I think I need to use a parenthesis in here or use this one. 2 divided by 3 and then use this. Okay. And equal to, it's 17.94. So let's say that it is 18. Okay, that's 18. So that means SH is equal to 18 times 1.5 times 10 to the 11. So that means 27 times 10 to the 11. So 2.7 times 10 to the 12 meters. That's the full distance. In any case, let's talk about this geometry again. So it is, this full distance is 2SH. It's the full major axis length. That distance is RP. So let me use the blue colors for these, RP, and that's RA. Okay. So that means 2SH is equal to the sum of these two distances. So therefore, this is like 5.4 times 10 to the 12 meters. RP is 8.9 times 10 to the 10. So that means RA is equal to 5.4 minus 0.089 times 10 to the 12 meters. So that's going to be like, yeah, I don't know, 5.3 times 10 to the 12 meters. I mean, it's actually too far away from us. So let me just say this. SH is about 18 times, so therefore this is 36. This is about like 35 times the astronomical unit, and one astronomical unit is basically the Earth-Sun distance. Okay. In any case, it's too far away from us, and so at faraway distances, there's no vaporization of the water on the comet. So it's basically frozen again. So as a result, we don't see it actually. I'm not really sure about this, if they can see it with telescopes or not, but in any case, it's too far away from us. So it basically spends most of its time in these places in here, in this region. Okay, so what about the eccentricity in here? So for eccentricity, I have to use the geometry of the ellipse, okay? So it's something like that. So that distance is RP, right? In this focus, there's this sun is in here. This is the other focus that's empty, right? Let's say other focus. And that distance is also RP. So that distance is 2C. Okay. And that distance is 2 times the same major axis length. And the eccentricity is equal to C divided by SH. Okay. So what is C? Right, that's 2SH minus 2RP. Okay, so that's the equation. So that's SH minus RP. Sorry about that. I need to do this calculation like this, unfortunately. So let me say that this is 1 minus the ratio of that RP to SH. And let's just compute this. So that's 8.9 times 10 to the 10. SH was 2.7 times 10 to the 12. Yeah, let's just forget about the calculation because I have just done this calculation before. So it's like 0.96. It's very close to 1. Exactly when eccentricity is exactly 1, the orbit would be a line. And that orbit can only be attained by an object which is like in one-dimensional free-fall motion directly towards the sun, right? So it's very close to one. So as a result, it's in this orbit in here. Okay. Do you have any questions about this?
Sure.
Yes.
I read somewhere that the eccentricity of the line is infinity, isn't it?
No, it's not.
Okay.
No, it's equal to 1. There's also some kind of a relationship to a parabola, so you can kind of consider a parabola as an ellipse with eccentricity 1, but it's in a different kind of a limit. So if I just keep this part and this curvature the same, but you just move the other focus to infinity, then you can also get a parabola kind of a thing. I don't know if they are doing things like that in there, but I don't know. But eccentricity is basically a number between 0 and 1. It can never be infinity. It can never be bigger than 1. Okay. The distance to the moon is Earth-Moon distance 384. Yeah, let me write down in here 384 400 kilometers. The period of the moon is 27 days. So the question is, what is the distance of, let's say, TV satellites in Clark orbit? Some people call this as the parking orbit. And some people call these as geostationary orbits. Why do they call it Clark orbit? So Arthur C. Clarke was the first one. So he's a science fiction writer. He's the first one who mentioned about this kind of a thing. So the basic idea is this. You know that the Earth is rotating, so that's Earth. Earth is rotating. Okay, we know that it is so. So in any case, so for nearby orbits of satellites, the satellites are also orbiting around the Earth. But if we just look at it, the satellites from our reference frame, in our reference frame, we are at rest basically. We will be seeing the satellites to be moving. So as a result, if you want to use this satellite for TV broadcasting, this is basically is not something that's nice, because the satellite will appear there and then you just have only a few minutes of time to watch the TV, and then you have to follow the satellite. That's too impractical. But somehow Clarke said that, well, there's a particular orbit actually. So if the orbital radius is such that there's a particular orbital radius in here, let me call this as RC. In that case, the period of the orbit is basically 1 day. And if these satellites are basically just above the equator, they are rotating around the equatorial plane. So since we are also rotating in the same way, right? So our period on the Earth is also 1 day. So relative to us, the orbit will basically appear to be staying at the same location. Okay, so these are called geostationary because relative to us, it appears at rest, right? So whatever the satellite in here is, like Turksat, for example, it just appears there. So as a result, when we actually set our satellite dishes, we just fix the dishes like that. We don't move the dishes around anymore. because the satellite always remains at the same location relative to us. It's basically is in an orbit around the Earth, actually, right? It's just an ordinary satellite, but its period is exactly 1 day, and we would like to find that distance. Okay, so I just gave some additional information about the period of the moon, because, yeah, I would like to compare the motion of that satellite to the motion of the moon, because moon is also a satellite of the Earth. It's not an artificial satellite, it's a natural satellite. So let's just call that distance in here like that. So that's the radius of the moon, that's given. The period of the moon is given, so that's 27 days, all right? And so as a result, by using this, I can solve this problem. Okay, so as a result, I need to compare the moon with this satellite. And the result would be like the semi-major axis length of the moon. That's basically the radius, because these are almost circular orbits. Clark orbit is exactly circular. That's cube. Let's see, I need to find the distances again. So therefore, like this is like Tm over Tc to the power 2 over 3. That is basically Rm over Rc. So the nice thing in here is this is 27. And 27 is the cube of 3. And so I know that this is cube of 3. So the result is like the 3 squared, so that's equal to 9. So therefore, the radius of the Clark orbit should be the radius of the moon's orbit divided by 9. So this is like 384,400 kilometers divided by 9. So now I have to divide this by 9, but I won't. Let me just do it in here. So 384,400 divided by 9. So it's like 42,000 kilometers. All right. Yeah, yeah, whatever. I mean, so let's just remember that the radius of Earth is like the 6,400. So as a result, it's like 7 times bigger than, it's like 7 times the radius of Earth. Right? Did I do the calculation correctly? It's a little bit smaller than 7 times, perhaps 6 to 7 times the radius of Earth. So these are too far away. Most of the satellites around orbiting around the Earth are very close to the surface. So their orbital radii are close to the radius of the Earth. So these are also called low Earth orbitals. But these TV satellites, they are too far away. And because of that reason, they also do not get affected by the air friction and things like that. So since they are too far away, but they are affected by some other things like the radiation coming from the sun and things like that, right? In any case, that's one actually knowledge that you might want to have. These orbits have actually are very far away from us. I think GPS satellites were also closer to the Earth. Okay, yeah, there was this question that I asked you. So, how do you measure the mass of the moon? Okay, I don't know if you have thought about this, but let me just say this, all right? Yeah, let me finish this because I don't have much time left in here. I have to finish right now. So if there's a discussion, if you want to discuss this, then we can discuss it after this.